Today we are going to look at two different ways of finding exact values for diodes that are in circuits, especially series circuits. There's actually a couple of ways we can determine the exact value, and we're going to look at both of them. So first of all, we're going to look at a series circuit. We have a resistor, a voltage source, and there's some current going through the diode and a voltage drop, and we don't know what it is as yet. So we can solve for the diode voltage and current basically using the relationship between the diode and the circuit itself. So first of all, we can use KVL, and we can write an equation that describes the circuit. We can just take the voltage drop Vs and subtract ID times R and subtract whatever the voltage across the diode is, and we get 0. So if we rearrange that, we can rearrange that into the y equals mx plus b format that we use when graphing a linear equation. This will be linear. So the slope would be minus 1 over r, and then the y-intercept would be Vs over r. So we have that equation, and then we also have the diode equation. So the two equations that we're going to use the original KVL equation that we found with the diode circuit, and then we're going to use the diode equation, which also relates the voltage of the diode and the current. So we have two equations and two unknowns, and we can solve this two different ways. We can do it graphically, and when we do it graphically, that means we actually are going to obviously graph the two equations, and we can solve it iteratively, which is actually how simulation problems are solved. So first of all, we're going to look at the graphical method, and then we'll look at the mathematical method in a minute. So first of all, we have a diode curve, and this is what makes the graphical method work, is that you actually do have to have an accurate diode curve of your diode. This can be attained either by taking the diode and just measuring the voltage and the current and plotting it. It can be created from the diode equation, where you graph it using the diode equation. If you know reasonably accurately the value of eta and the thermal voltage, you can make a reasonable accurate diode equation. You also have to have the saturation current. So this can be done either by graphing it manually, or you can use a curve tracer, which just basically spits out the curve for any given diode when you plug it in. That can be done as well. So we have a characteristic curve for the diode, and then we graph the linear equation on the same axes. And when we do that, we get the line that extends from the y-intercept, which, as you can see, is Vs over r. So that would be the point at which the line intersects the vertical axis. And then it actually intersects the horizontal axis at Vs, because if you set the current to 0, this is what you're going to end up with. You're just going to end up with the voltage of the diode being Vs. So that will work. And then we also can look at the slope of the line, which is minus 1 over r. So we can actually determine what that slope is relatively easily if we know what the resistance of the circuit is. So we got those two graphed, and the intersection point is where the circuit is actually operating. So the intersection point is found as being the operating point, the Q point, and the Q point actually, the Q comes from the word quiescent, and that is not used so much. We call it the operating point or the bias point now, but that's where the Q originally came from. Once we have this, we can actually read the diode current directly off the graph by just going horizontally to the vertical axis, and then we can read the diode voltage as well. And that gives us the exact diode current and the exact diode voltage for this particular circuit. The difficulty with this is that the graphical method has a couple disadvantages. First of all, you really do need an accurate characteristic curve for the diode in the circuit, and that sometimes can be hard to obtain. You also are limited in your accuracy as to how well the graph can be read, so how good the resolution of the graph is. And admittedly, the previous graph was not to scale at all because it really showed the voltage of the diode being halfway to the source voltage, and really that's not the case. Usually the diode voltage is around 0.7 and the source voltage might be 10, so you lose a lot of resolution when you do graph those together. So the other method we can use is the iterative method, and the iterative method is mathematical and it's very accurate. The way we do this is we make an initial assumption of what the diode voltage and current might be. And that's always a little scary because we have to make assumptions and sometimes we don't know what those assumptions should be, but we can usually assume a diode voltage, if it's silicon, of about 0.7, and then we can make kind of a guess at what the current might be initially, and then we use the diode equation to come up with a more accurate value of both, and then this is just repeated until a proper value is determined. To do the iterative method, we're going to start with the diode equation, and we're going to look at it at two different points on the diode curve. We're going to assume there's a forward bias and that eta equals 1. And you'll notice that the equation's a little truncated, and that's because we're going to take the -1 after the exponential function off because it doesn't matter. We're going to be in forward bias mode anyway, so we will not need to worry about that. It'll make the calculation easier. So we're going to divide ID2 by ID1, and we get the equation on top and bottom. You'll notice that the saturation current appears both places, so we can actually eliminate that, and then we're going to combine the exponential functions and get one value of e to the VD2 minus VD1 over the thermal voltage. We're going to take the natural log of both sides, and when we do that, we get the natural log of ID2 over ID1 equals VD2 minus VD1 over the thermal voltage VT. Rearranging, we end up with the difference between the voltages is equal to the thermal voltage times the natural log of ID2 over ID1, but frequently we're already going to know that first diode voltage. So really we're using this equation to solve for the second value. So we're going to move that around a little bit, and we're actually going to change it to a base 10 log for no reason whatsoever other than we just are, and we get the second diode voltage is going to be equal to the first voltage plus 2.3 times the thermal voltage times the log of ID2 over ID1. So let's look at an example and use that. We have Vs is 5 volts and R is 1 kilo ohm. We're going to assume that the diode current is 1 milliamp and the diode voltage is 0.7 volts. We make the diode voltage assumption on what we know about the approximate forward voltage of a silicon diode. We make the ID1 assumption based on no reason other than it's just a cool number and it's convenient. So that's why we're using that. So we use the linear equation from the circuit to solve for ID2. So we just take the source voltage, subtract our initial assumption for the voltage, and divide by 1,000. We get 4.3 milliamps. Then we use the iteration equation to find the second diode voltage. And when we do that, we plug in the numbers and we get 0.736 volts for the second voltage. And now we take those values, ID2 and VD2, and to do the second iteration, we make those ID1 and VD1. So we have ID1 is 4.3 milliamps, VD1 is 0.736 volts. And now we're going to solve for ID2 again, using the linear circuit equation and the new value of VD. So we go through, we take 5 minus 0.736, divide by 1,000, we get 4.26 milliamps, pretty close to 4.3. And now we do the iteration equation again to get a second value for VD2. And when we do that, we actually end up with the same value. So because the second voltage didn't change, we don't need to do any more iterations. We're close enough that we don't need to really worry about doing any more. So we really don't need to do this very often. In reality, unless we really, really need superior accuracy, we don't do this. We usually just use a better model than the ideal model. If we use the ideal model, but we reflect a more realistic voltage drop, then we can actually get reasonably accurate results without going through the iterative process. For silicon diodes, the actual drop is around 0.7, so the constant voltage drop model uses that value. We can adjust that model for other types of diodes that have different voltage drops if we wish. The difference between the two is really, really small. You'll notice that for the actual diode curve, you do have an area below 0.7 volts where the value fluctuates a bit. And in the constant voltage drop model, the forward voltage is 0.7 volts or it's 0. So if we use the constant voltage drop model, we actually, if we have a forward bias diode, we replace that with a voltage drop. In the ideal model, we replace the forward bias voltage or diode with a short circuit. Using the constant voltage drop model, we actually replace it with a voltage source that has a drop of 0.7. So if we look at this model and you do the problem that we just did using iteration, and we just assume that the diode voltage is 0.7, we do get really, really close to the current we got before. That was actually the first iteration we did. And 4.3 milliamps is really close, within 1%, which is great. If we were to use the ideal model, then we actually end up with a value of current that is really, really far off from what we had. So in this case, we actually end up with about 15% difference. So that is really not a good model to be using. So most of the time when we analyze diode circuits, we're going to use the constant voltage drop model. Again, just like with the ideal model, the tricky part is deciding which diodes are forward and which ones are reverse. But once we figure that out, we're going to replace the forward bias diodes with a voltage source rather than just a short circuit. Reverse bias diodes are still replaced with an open circuit. And as with the ideal model, once you've made your assumptions, if KVL or KCL or the diode characteristics don't work, then we have to go back and look at our assumptions again.